Good morning, chemistry friends. Here we go. We are going to start a new unit today on reaction rates and equilibrium, starting with chemical kinetics, which just talks about reaction rate. I'll get to that in a minute. Let's update for a moment where we're at. Yesterday, we wrapped up the gas law exam. You had a unit exam to take. You had two options between 9 and 10 a.m. and between 1 and 2 p.m. And that went well for most. I apologize for the 1 p.m. didn't drop automatically, and thank you to all of you who quickly sent notifications and stuff. We got that going. I don't know why it didn't drop automatically. It was set to, but then I extended the time, the hour. I extended the hour to include that time that you had missed, and I think that worked out for most folks. As usual, there were some internet issues with some folks and everything else. And on today, Wednesday, April 22nd, you'll have an opportunity for a third option. I'll get that going this morning and fired up for you to do so. And that'll work. I did want to address a couple things, and I want to be careful. I want to be careful a little bit because I know that there are many different situations, and that's why I say when you have issues with things, contact me right away. And that's why I also said I'll deal with things on an individual basis if there are issues, because some people are very busy during the day and have opportunity, have things that they are responsible for above and beyond school that they normally wouldn't be if you were in the halls of Eastview. And we respect that, and I want to work with that. And those people we have worked with throughout this distance learning, and they usually contact me at some point during the day when they have a minute, and we can rearrange things. Some of you, I know, maybe don't necessarily have some of those obligations, but somehow your shift, in some respects, you're still on I'm in school all day and then in the evening I do homework shift, but that is now shifted to I'm not in the building all day, or maybe I do a couple of, but I really don't check my homework till the evening and stuff like that. And then I miss things. Be careful that you're checking in during the day, every day, and if things are going on, because I'll be honest with you, after staring at the screen all day, this is a different mode even for your instructors. After staring at the screen all day, I generally shut down after 3 o'clock when the duty day is done, because I just can't stare at the screen every day. So if, for the most part, although I might check once in a while, if I have a late afternoon or evening meeting, I might just pop in and do stuff and check and maybe respond then. But for the most part, if you're doing something and have an issue and it's not during the school day, you're not going to get a response till the next day. And I say that in part to A, not panic. I will respond to you, but B, just know, besides what we're doing during the day and staring at screens and office hours and everything else, I have plenty of things with coaching and teaching and a CIS course with the U, where I'm actually working and in Zoom meetings in the evenings. And so there's times I need to step away also, just as you do. I also know that I got some emails yesterday of people who did not tune in right away, like a 1 to 2 exam, and they don't start taking an exam till 1:45 or something, and the time gets cut off. If nothing else, I've inundated you with communication, videos every day explaining everything, updates every day under the announcements page, the daily calendar folder, which you can go in and check every day as to what we're doing, similar to when I had your study guide and had stuff going on like that. Not quite as robust yet as when you had a study guide, but there. Telling me that you didn't know a timeline or opportunities, what time they were at and stuff, it just doesn't fly. It just, all it tells me is you're not checking every day, and maybe you're not watching the videos, maybe you're not doing everything thoroughly so you can be the best you can be. And please don't do that, okay? When I see those emails with all the communication, everything I put out in video so you know what's going on every day, saying I didn't know something, it just doesn't fly. You just can't support that. So please don't. All right. So we're all in this together. I'm trying to be flexible, but still hold a certain level of responsibility to juniors so that when you do graduate and get on to school and everything else, that you have good habits. Communication will be the key. All right. You've had enough time to kind of watch this first slide and laugh a little bit with Calvin and Hobbes. Really, here's what we're doing here. Short thing, couple of videos. You're going to watch this. That's an outline notes of what we're going to start doing. And then I have some demos on another film that you're going to watch today. And then we'll start looking at some lab stuff over the next couple of days that I've filmed. Anyhow, all this is talking about reaction rates. Some reactions go fast. Some reactions go slow. Some reactions are in between. It's something you can time and keep track of. And probably more the key to this is if you have like ammonia, one of the top 5 chemicals produced in the country because it's used in so many things, fertilizers, cleansers, all sorts of stuff. But commercially producing ammonia, initially where the yield of ammonia you get and how quickly it goes is not outstanding. And so how do you make a lot of money when you don't have a reaction that, is, as we say, not outstanding in its initial setup? You find things to change. You find ways to speed it up and drive it to make more ammonia. And that's kind of what we're talking about is how can I speed things up? How can I slow these down? Now, as we get to these factors, you're going to see here in a short bit that all we talk about is speeding up. But for the most part, it's just the opposing function to slow it down, because sometimes you want to slow it down. And the key to all of it is a theory called collision theory. Okay. For a reaction to occur, the particles must have enough energy and collide at the proper orientation. Okay. So enough energy is something called activation energy, and we're going to see that as we go through this slide. Every reaction has one. They have to overcome a certain hill, and I'll point out when we get to the graph that they have to overcome for the reaction to occur. Okay? And that doesn't matter whether the reaction is something called spontaneous, where it's going to occur and who knows what time is, or non-spontaneous and you have to drive it. Doesn't matter. For any reaction to go, it's based on collision theory. The particles that are in that collision, the molecules that are in that reaction, when I put the reactants in, must collide with each other at proper energy level, activation energy, to form what's called a transition or an activated complex. And then once they do that, then it goes. Then it goes. If they get there and they're in the right orientation, then it goes. And then whether it's a reaction that absorbs energy or like most gives off energy, then it's just going to go. And so as we look at reaction rate and the factors that affect it, one of the things we're going to talk about all the time is how does that improve the chances of collision theory? How does it improve the ability to collide at the appropriate energy level and orientation? Or conversely, if you want to slow it down, how does that lower that chance of collision theory, of getting to the appropriate energy and orientation? Okay. And let's show you this picture, and I'll try and move my ugly face out of the way if I can. You see 4 scenarios here. In A, you see they're colliding with each other, but it's not the proper orientation, so they just bounce off, and it's no big deal. That happens all the time. Okay. Here, again, another incorrect orientation. They collided into each other, and they possibly could have had the appropriate energy level, but they weren't in the right orientation. In fact, I would say they did have the appropriate energy level, but the orientation was there. Now, What I see here is I see a collision. They're oriented properly. They are at the appropriate energy level. They make what's called in very brief microseconds an activated complex, and then you get your new product. So whether that's a synthesis reaction, a combustion reaction, double single replacement, decomposition, whatever it is, this has to occur. This will occur briefly, and then it'll go, and the new products will form as they change bonds, switch around, and do the things they have to do. In the last scenario, what you see is they are colliding in the proper orientation, but they don't have enough energy. They're not at activation energy, so they bounce off. So C is the ideal spot that we want to be at. Okay, and then the reaction will occur, and it'll just go, and it'll go until it's done or it reaches equilibrium, which we'll talk about later. Okay, so overall on reaction rates, kinetics just says how fast does a reaction proceed. And again, some are fast, some are slow, some are not. You may want to speed them up, you may want to slow them down. That's what we're looking at today. Okay. Reaction rate itself is the change in concentration of a reactant or a product with time. And basically we talk about reactants. If you think of a reaction, and I have a slide soon that'll show you this. When I mix things, there's that momentary second when there's nothing but reactants. Okay. And whatever, I put the two reactants together and there we go. How they measure reaction rate most of the time is then as the reaction proceeds, you can draw off a sample at different time periods and you check the concentration of each of the substances. And what you'll see is the reactants, the concentration keeps going down because they're getting used up and you have a reaction going. You'll see the products start from 0 concentration and then start increasing because you're making more products. And so they measure that, and then they talk about, when they talk about reaction rate, they talk about that change in concentration over time. So molarity per second, moles per second, something that talks about that concentration. And then you can consider, and then that's what you look at. So say we had a reaction where A went to B, just a general thought, okay? The rate then is going to be how much the concentration of A changes over a certain time period. And I'll talk about the negative side in a minute, okay? All right. So the change in A's concentration, its molarity, over however long a period you're going for. And that's usually measured in seconds. B then is my product. I could also measure the appearance of B. Okay, although most people start with the reactants just because you know you have them. You're 100%, it's all reactant. Okay. And that's no different. That's going to be the change in your product concentration over time. And again, it's just taking samples out of the reaction vessel and measuring the concentrations. Okay. Now, why is A negative? Why is A negative? Because you start losing reactants over time. When the reactants occurring, your reactants are going down and your products are going up. So that rate is going to be negative. Okay. It doesn't mean negative as in below 0. It just means I'm losing. Okay. Where B, your products are going to be positive because you're gaining. That concentration is going to keep getting bigger as you add more product. So that's the basic kinetic theory. Okay. And here's what I told you. Here we are at time 0, and you can see by the color of the dots that we are all reactant. Okay. And then as you get over time, you see I have less dark reactant dots and more red product dots, and that keeps increasing. Now here, after it's been, if you guess this clock, a minute or whatever, now I'm almost all product and a little bit of reactant. And that's all we're talking about. The rate at which over time, how much of this changes. Okay. And that's what there you go. Here's my A reactants. And over time, I started with, say here, 40 molecules, and and there's 30, there's 20. See, these would be time factors at seconds where I took out a sample, took out a sample, took out a sample, and measured the concentration. I can do the same thing with B. So you can see that the reactant concentration goes down, and that's why that's a negative change, rate change over time, and the product goes up. Okay? And again, all you're doing at these different time intervals is having a sample withdrawn, and then you analyze it for its molarity, and then you can measure that change. Okay, and that's where you get that rate factor from. All right, now let's talk about the factors. We have 4 of them that affect the rate of the reaction. One of those is just concentration. Okay, and you can see in the little graphic down here, and it goes back to collision theory. The less particles I have to react, the lower your frequency is going to be for colliding at the appropriate energy level, proper orientation, and so I'm going to have a slower rate. If I want to increase that rate, then I can add more of a reactant substance. You know, if I'm mixing 2 things, I can add more of both or add more of one or whatever. But the more particles I have, as I've increased the concentration in this final one, the more greater chance I have of colliding at the appropriate energy level, and orientation and reaction will go faster. I just have more particles colliding. And that's why this says, if I increase the concentration, I'm going to have more collisions. I'm going to have a better chance of colliding with proper energy and orientation. Doesn't guarantee anything. It will most likely speed up, or odds of speeding up, and it will speed up, because I've just given collision theory a better opportunity to succeed. Okay. Now, I didn't do another slide because it's the same thing. If I wanted to slow it down, then I could dilute it out, lower the concentration. So everything that we say with increased concentration, just flip it opposite if you want to talk about slowing it down. Lower the concentration, say by dilution, you'll have less collisions, and you'll have a lower chance of colliding with the proper energy and orientation, and therefore the reaction rate will be slower. Now, I put this picture over here also because people ask about gases and pressure. And pressure, again, only affects gases, so this would be a gas thing. Pressure changes are really a concentration change when you talk gas. Because if I increase the pressure, I'm lowering the volume. And so while technically I'm not adding or losing more particles or whatever, I'm not adding more particles, but I'm putting those particles in a smaller volume. So if you remember your concentration, it's going to be, you're getting more concentration because you have less space, not because you're adding particles, but you have less space. So again, you're increasing the opportunity for collisions in that smaller space. So that only is with gases, but that's another way you can look at concentration. If it's a gas, okay, like the whole ammonia deal. Ammonia, when you make ammonia, it's all gases, all mixing nitrogen and hydrogen gas, mixing together, make ammonia. One of the ways I can increase that rate is just increase the pressure, because then the volume gets smaller. We just learned that with gas laws. So that, by changing the volume, I change the concentration. Okay. So that's one factor, and we will be demonstrating a concentration thing in the demo video, and you'll enjoy it, I hope. The next one is temperature, and I don't demo this on the thing because it kind of makes sense. Temperature is, if you remember by definition early in the year, the average speed of the molecules. So, you know, you can see in the graph here, and this gives you an idea of what we talked about reaching activation energy. Okay. Anyhow, if I increase the temperature, they have more kinetic energy. They're moving faster. You're going to have more collisions because they're bouncing around inside the container faster. They're going to collide more often. And of course, because they're at a higher movement, higher speed, higher energy level, their chance of getting proper energy and orientation is much greater. And so that's why when heating things up, you get a faster reaction because the particles are moving faster. You're getting more collisions. You're getting more collisions at the proper orientation energy level. So as you can see by the little graph here, you are getting more successful collisions, you've increased your chance. And again, same thing with cooling something down. If you cool it down, you slow it down. If you slow it down, you have less collisions. If you have less collisions, you have less of a chance. Okay. And so it'll slow things down. All right. We don't demonstrate that. Well, I shouldn't say we don't demonstrate it here. We demonstrate it in the lab we're doing that I have filmed for you. Factor number 3, and this is one that gets I shouldn't say it's confusing for chemistry students. They understand it, but they don't explain it well on exams. Surface area, okay? And here we go. And you know this. If I put a big chunk of ice out on my driveway to melt, it will melt. It'll take some time to melt, but it will melt as the light is hitting the outside surface area, because surface area is just what it is, what's exposed on the outside. I have a boatload of areas, particles in here that aren't exposed yet. But if I were to take this block and chop it up in my driveway, say it was that big chunk of ice block in my driveway, if I chop that up and expose more surface area, exposing more of the particles that are in there, it's going to melt faster. Okay. So that's the idea of surface area. And think about this, you're building a bonfire in your backyard. You don't start with a big old log, right? You start with kindling because it has more surface area. So you might take a branch, but you break it up into smaller pieces and use that as kindling. Okay. It doesn't change the number of particles. It just changes the number that are exposed to be able to react with. So there's more particles to go with because I've exposed all the inner stuff and that's not there. So if I increase the surface area by taking a big chunk of something and chopping it up, again, I'm not changing the number of particles. I'm just changing the number of particles that are exposed to be able to react. I'm going to get more collisions. I got a better chance of colliding at the proper energy and orientation. This is a fun demo that you'll see in the video. Okay. And again, conversely, if I want to slow it down, then I would use stuff with a bigger surface or less surface area. If I wanted to slow the reaction, I would use the big chunk as opposed to breaking a big chunk up. Okay. And then the last one are catalysts. And in biology, you would have talked about catalysts as enzymes. That's the word, and that's what they are. Catalysts can only do one thing. They can only speed up a reaction. You cannot, of all the 4 factors, catalysts can never slow anything down. They only increase. Okay. The other key to catalysts is they are not consumed in the reaction. Really what catalysts are is it is a compound that helps the orientation. If you think of biology and enzymes, okay, you've got a substrate that comes in and it binds to the enzyme, and the enzyme exposes its binding site, its orientation, so that it can connect with the other molecule in there and have the reaction go. That's what we're talking about here. Okay. Catalysts help the orientation. And by helping the orientation, then, if you're at sufficient energy and you orient it better, then it's going to go much faster. And this graph kind of shows it. You can see the reaction progress without a catalyst. You can see the energy hill to climb is way up here, the activation energy, and it's just going to take longer to collide at that energy level with the appropriate orientation. The catalyst helps the orientation, which in a sense lowers the activation energy. And that's what they talk about when they talk about catalysts. They lower activation energy. And they do that because they're assisting the orientation. So it really takes less energy in a sense. And that's the easy way to say it. There's a lot more to it if you got into the complexity of chemistry. But if you lower that energy then with a catalyst, then it's going to proceed much faster because it doesn't need as much in the collision to get there. And part of that's because it's been oriented properly. I like this graph better. This shows you really what we're talking about. Any reaction will have a certain amount of energy and the time that it takes to do things. Every reaction will have this activation energy hill, the height of which is based on the specific reaction. You have to collide in the proper orientation energy level to get there. And then after that, the reaction, you can see the reaction just dumps downhill quickly. Okay. So that's what we talk about activation. In collision theory, if you're going to have a reaction occur, the particles must collide at this energy level in the proper orientation, and then the reaction just goes. Now, this doesn't say how fast it'll go. It just says it'll go. Okay. By using a catalyst, you can see what I've done is essentially I've lowered the activation energy. And so it'll proceed much faster because many more of the collisions will occur at this lower energy level, speeding it up than would at this higher energy level. And the reaction will go. All right. So that's that's really most of what we need to know about reaction rate. It's the change in concentration over time, which you can do by getting the reaction going, pulling out samples, check the change in concentration of your reactants, and set up the rate of that thing. Then you can speed up or slow down with a few different factors, changing concentration, temperature, surface area, or using a catalyst. Okay. And that's what we're going to do in our demo, and that's the things we're going to look at in our lab. Anyhow, that gives us our basic knowledge of where we're at as far as reaction rate notes. Your next job then will just be to watch the reaction rate demos I put together that show you concentration, surface area, and catalyst. And I hope you enjoy it. Anyhow, be safe, have a good day, and we will talk at you very soon.